In this video, we're going to be talking about graphs of rational functions. And although a rational function is just the ratio of any two polynomials, we're mostly going to be concerned with pretty simple ones, like 1 over x and ones related to that today. So we're going to start by making a graph of 1 over x. And I'm just going to copy in a table of values for you. And say, doing 1, 2, and 4. Those are numbers I know how to take 1 over them and get a good decimal. And I think what I'm going to do also is I'm going to make the scale 2 ticks for each unit. I think that'll make your graph look a little better, so I'm going to do that too. And then I'm just going to plot some points and connect some dots. So 1, 1, 2, a half, and 4, 1/4. Okay, that gives me some graph, but not the most. It's kind of like, well, what's going to happen with the rest of it? But maybe I'll go over here and I'll see something else. Well, -1, -1. It's going to really kind of give me the same picture. -2, -1/2, and -4, -1/4. Okay, so it's like, okay, I'm seeing the same thing over here. Okay, and you just got to think about, okay, what's going to happen kind of between -1 and 1. Let's start with 0. So if I plug in x equals 0, I'm going to get y equals 1 over 0, and that's not defined. That's not a real number. So I'm going to say does not exist. And I guess we'll come back to that in a second. So I'm going to have to think of something else between -1 and 1 that isn't 0. Well, maybe I'll do a half. Okay, if x was a half, then y would be 1 over a half, and that would be 2. Okay, so a half and a 2. Okay, so that's good. And we know that when you divide by a smaller number and you keep the numerator the same, the quotient's going to be bigger. Kind of without limit, right? That if we were to just like make x smaller and smaller, we'd be getting a larger and larger quotient back, really without limit. So I might say a fourth will give me +4. And then I can see I've got something like what we might have called in a previous unit a vertical asymptote here. And the same thing's going to happen over on the other side. So that when x was -1/2, y would be -2, and then when x was -1/4, y would be -4. Just assuming it's got the same scale, 2, 4, 6, yeah. Okay, not the best sketch ever, but pretty decent. And so this is going to be the graph of 1 over x. So on the domain range discussion, domain, that's the set of suitable x values that I can plug into my function, okay? And we saw that 0 was not going to be a suitable value because it caused us to divide by 0. And so the domain of this is really just x is not equal to 0. And also show that by, kind of coloring in the vertical asymptote here. And we're going to see that pretty repeatedly with these rational functions, is that they oftentimes have a vertical asymptote on their graph that correspond to 0s in the denominator. Okay, but then there's also something going on with the range. Okay, and notice that over here with the range, well, y is getting closer and closer to 0 the farther out I go, the more I divide, the less I'll have back. But it's never actually able to equal 0 because the numerator is fixed at 1. Okay, and a fraction can only ever equal 0 when its numerator is equal to 0 and its denominator is non-zero. So I'm going to say over here, this is a horizontal asymptote, kind of like we saw with those exponential functions, because something like 1 over x can never equal 0. So I'm going to say y is not equal to 0, and then I'll just write in a couple of reasons here. And then, we're not really talking about this yet, but I am going to point out that the things that are outside of the domain and range, they are going to correspond, at least even for the range in this class, not true in maybe in pre-cal next year, they'll correspond with the equations of the asymptotes. We'll talk about that more in a second. Okay, next, we're going to want to sketch the graph of y equals -1 over x. I kind of want to leave the original graph visible mostly, because just think about it. The only difference is I'm taking -1 divided by x instead of +1, so all of these would just become the negative of what they were. So I'd have like -1, -0.5, -0.25, but then +1, +0.5, and +0.25. So really that means that this kind of arm of the graph is going to go down here, and then this one would flip up there. And we don't need to draw a super accurate graph of that. I can just say, okay, make sure to label my axes. And then I can say, all right, well, the original 1 over x was in here and there in those two quadrants. So negative 1 over x will be in the opposite quadrants. Yeah, that's probably not my best sketch ever, but that's the shape of the graph. All right, let's see what else we got here. Okay, finding the domain of a rational function. Yeah, I think in general my advice is going to be that since the domain of a rational function is just everything that doesn't cause division by zero, you can find that by computing the zeros of the denominator. And then we're going to exclude those values. Okay. And then just to review all of our polynomial rules, our domain rules. For polynomial, you can plug in anything you want to a polynomial, so the domain is all real numbers. For a radical function, for something like the square root of u, where u could be like 2x plus 5 or some sort of expression, that's going to give me u needs to be not negative, right? Because we're not going to take the square root of a negative number and get a real number back. Okay, for exponential, the domain for that was all real numbers. We just kind of talked about that one in the last unit. But for the log functions, you've got the log base b of some algebraic object u. What we did was we grabbed u and we set that strictly greater than 0. Okay? And so now we've got another one for rational. We're going to grab the denominator and say it's not equal to 0. So it's kind of different for each one. For radical, it's greater than or equal to. For log, it's greater. And for rational, it's going to be not equal to some values. And, maybe I'll do a quick example here. No need, it's below. Okay, so finding the range of a rational function. For now, especially in this class, it's really going to come back to the idea that 1 over x can't equal 0, or non-zero divided by non-zero can't equal 0. Okay, and so we're just going to remember that y, and all of the functions that we're going to deal with today are going to be just having a number in the numerator. Next time in the next lesson, I'll show you what to do if you end up with linear on top and linear on bottom, or even quadratic on top, quadratic on bottom. We'll be able to deal with that then, but for now, really just going over, like 1 over x cannot equal 0. Okay, and then the range will come from that, and I'll show you what I mean here. So let's look at these two examples. Set first. All right, so first of all, find the domain of f. One more time, yeah. All right, so what we're going to do is we're going to take the denominator and we're going to find its zeros. So I'm going to factor that by finding two numbers that multiply to 3 while adding to -4, and I feel like that would be -3 and -1. And then that would give me x equal to 3 and x equals 1. And these are numbers that if I plug them in for x, it's going to cause me to divide by 0. So I'm going to say the domain of f is going to be x is not equal to 3 and x is not equal to 1. Okay. Maybe next time when we go to graph something like this, we'll see that it has 2 vertical asymptotes. Okay. And then g of x is going to be 2 plus 3 over x minus 4. Find the range of g. Okay, so this one's a little more than I've given you so far, but I'm just going to start off with the fact that x minus 4, regardless of what x is, that can't equal 0, right? So 3 over x minus 4 cannot equal 0. Therefore, 2 plus 3 over x minus 4 can equal anything besides 2 plus 0, which is 2. So we're going to say y can't equal 2, because that's just basically saying g of x can't equal 2. So the range of this thing is going to be y is not equal to 2. And then if we needed to write a horizontal asymptote, the equation would be y equals 2. But we'll talk about that in a second. All right, so now let's define what we mean by these asymptotes. So an asymptote of a graph is a line where the distance between the graph and the line approaches 0 as one or both of the x or y coordinates approaches infinity or negative infinity. So it's something that we're getting like arbitrarily close to the farther the graph goes in some direction. We've seen this a couple of times, but that's going to be our definition. So for a vertical asymptote, I'm going to just kind of bring up some function we haven't talked about yet, maybe like 1 over x plus 1. Okay. What would cause us to divide by 0 here would be x equals -1. The domain would be x is not equal to -1. And so this is going to look very much like the graph of y equals 1 over x, except it's going to have that vertical asymptote that was on the y-axis. This will be at -1. So effectively, this plus 1 in there has moved the graph of 1 over x to the left by 1. And really what I'm going to do here is I'm going to label my vertical asymptote. And one thing that I just really wanted to point out is that, you know, an asymptote is a line. It's like the very beginning of the definition, and a line has an equation, so if they ask for the equation, you need to, for an asymptote, you need to give an equation. Right? I'm going to try to remember to make sure to ask for the equation of the asymptote, but even if I just ask for the asymptote, you need to know that that's going to be a line. You need to give me an equation for it. All right, so then it's going to be, whoops, and I guess that's all right. Okay, and that'll be my graph. Okay, so to recap, vertical asymptote is caused by dividing by 0, and it's a vertical line, so it's going to have an equation like x equals some number. For horizontal asymptote, okay, what we're going to see this look like would be y equals 1 over x, like, you know, plus some number on the outside. So I'd say, I don't know, like plus 3 or something. I've got a couple of examples down there, but I just kind of do one in line. Okay, so what's going to happen here, if we did the range, we'd say 1 over x can't equal 0, so 1 over x plus 3 can't equal 3. And so y equals 3 is going to be my horizontal asymptote. And I'm going to just kind of label that. All right, that made it look like -3. Maybe I'll just extend that tick mark. All right, and then the x-axis should probably be about there, and then the graph is going to otherwise look the same. It just got shifted up by 3 because of that addition of 3 on the outside. So I'm going to go like that. My same, you know, standard 1 over x graph, just shifted up by 3. And it's going to have a vertical asymptote at x equals 0, because if I plugged in x equals 0, that would cause division by 0. Right, so the things to remember is really, in this class, when we let in the future, when we let the numerator have zeros as well, there will be times where a horizontal asymptote can be crossed. We're just not going to be dealing with that in Algebra 2. We'll just save that one for pre-cal. We're going to say that the horizontal asymptote is caused by the fact that 1 over x can't equal 0. And if it's a horizontal asymptote, it's a horizontal line that's going to have an equation like y equals some number. Okay, so let's do a couple of these and then sketch the graph of the function and label the asymptotes. Okay, so 1 over x minus 5. Much like up above, I'm going to say that this has a vertical asymptote at x equals 5, because that would cause division by 0. So I'm going to actually write that down. And then the horizontal asymptote has to do with range. Okay, so 1 over x minus 5 is just like 1 over some number. That's never going to be able to equal 0. So I'm going to say horizontal asymptote, that's y equals 0. Okay. And then when I sketch the graph, go down here to do that. Okay, x equals 5. I'm going to really need to favor the x-axis in a positive way. All right, so x equals 5, that's my vertical asymptote. And then y equals 0, that's the x-axis, and you probably can't even see that I'm doing that. But you know, when that happens, I like to just like draw a little bit above it, so it gives it a little bit more thickness. And that'll be my horizontal asymptote, and then otherwise the graph will be standard 1 over x. Had this been -1 over x minus 5, then it would have been the -1 over x graph, and it would have occupied those two kind of corners. Ooh, that was a good one. Okay, now g of x equals 1 over x minus 2. Okay, the vertical asymptote would be x equals 0. And the horizontal asymptote is going to be y equals -2 because 1 over x can't equal 0, so 1 over x minus 2 can't equal -2. So I'm going to go in here, I'm going to draw my y-axis, cut it in half, and that'll be -2 right here. Right, that would mean that the x-axis would be up here, and then the vertical asymptote is x equals 0, so I'm going to clear that in. And then I've just got a graph after that. So regular 1 over x. So respecting those asymptotes. All right, now we're going to sketch some friends of 1 over x, with more than one thing going on. So I've got this x plus 3, which we saw is going to kind of move this to the left by 3. But we've also got a -2 here. So with the domain, we're going to grab the denominator, say that can't equal 0, so that will be x is not equal to -3. That'll mean I have a vertical asymptote at x equals 3. And the range, okay, well, -2 divided by some number, that could be anything except for 0. So I'm going to say y is not equal to 0. Okay? So the impact of the +3 was that it, changed the domain. It changed the equation of the vertical asymptote. It caused those things to, the excitement to happen at x equals -3 instead of x equals 0. Let's say that moved the graph left by 3. And then the -2, well, the negative means I'm going to have to draw the graph of -1 over x, so I guess graph goes upside down. And then the 2, well, if I have a 2 on top, the y-coordinates would be twice as big. So that'll end up being something we might call like a vertical stretch in the next unit. But if you're ever unsure, you could just like we did at the beginning, make a table of values, plot points, connect the dots. There's nothing wrong with that. So I go over here, x equals -3 is where my vertical asymptote is. So I might put that in here. That would mean that my y-axis would need to go here. If that's my x-axis, okay, -2 means it'll be the -1 over x graph, which will be on these two sides. And if it's -2, well, it'll be twice as far away, so I don't know, maybe I'll go like that. I'm not really committing to a scale in y, so it's kind of hard to say. All right, and then, y equals 0, I didn't label the asymptotes, so I'm gonna just put that in there too, just to be consistent. And yeah, that'll be my horizontal asymptote, y equals 0. All right, and then I've got one more of these examples. All right, 4 plus 1 over x minus 6. So I think it's always good to start with the domain and range. So domain, we're going to grab the denominator and make sure it's not equal to 0. Okay, so that means that x can't be equal to 6, right, if x minus 6 can't be 0. For the range, well, I know 1 over x minus 6 is not going to equal 0, so y can't equal 4 plus 0. Ooh, x-intercept, y-intercept, that's not something we've talked about, okay? Because sometimes these things don't have an x-intercept or a y-intercept, like with 1 over x, it had neither. But with an x-intercept, that's where y is equal to 0. So we're going to set y equals 0 and solve. I didn't leave nearly enough room to solve, so I'm going to go sideways here. So 4 plus 1 over x minus 6 is equal to 0. Okay, I'm going to maybe subtract 4 from both sides. I might write it as a fraction so I could cross multiply, but that doesn't really matter. Okay, so 4 times x minus 6 equals 1 times 1. It's 4x minus 24 equals 1. X equaling 25, and x equaling 25 divided by 4. Well, 24 divided by 4 is 6, so I think that's going to be 6 1/4. Okay, we found an x-intercept. It's kind of a lot, but that's part of why I showed you how to solve rational equations, so you could do things like this. Okay, and then the y-intercept, that one's easier to find. We're just going to plug in x equals 0, and y will equal 4 plus 1 over 0 minus 6. Well, 4 is, I should have left that as 25 over 4, but gone too far now. 4 minus a sixth would be 3 and 5/6, so that would be 23 over 6. Okay. The impact of the -6, well, that really changed the domain. I'm going to change the equation of my vertical asymptote. It caused it to go from x equals 0 to x equals 6. That's a right by 6. And then the 4 plus on the outside, well, it was like if we added 4 after the fact. It's going to move it up by 4, right? We moved our horizontal asymptote up by 4. Okay, so I think I'm going to sketch the graph. Okay, so I've got the domain, x can't equal 6, so 6 is kind of like the center of the action. And that would mean that I'm also going to need a lot of positive y here because the middle is like y equals 4. So I think that's kind of the drawing we need. Yeah. All right. And then maybe I'll label 4. Okay, so x can't equal 6. And y is going to not equal 4. But otherwise, it's just that same 1 over x graph. So I'm going to just draw that same one I've been drawing the whole time. And there we go. Now at the bottom, we've got this kind of a question for thought here. What would happen if the denominator was 2x minus 6 instead of x minus 6? And well, I think what would happen, I think the most obvious thing is when I go to compute the domain, that would be different. The equation of the vertical asymptote would also be different. So 2x minus 6 equals 0 at x equals 3. So that would bring this closer to the y-axis. And so also I'd have a 2 in the denominator here. It would be like, like a half in the numerator also. Because I could write this also, instead of 2x minus 6 in the denominator, I could write that as half over x minus 3. Yeah, I'll let you think about why that's true, but and then it would also have like kind of this vertical compression as well, in addition to this getting moved closer to the y-axis. But I think that's all I'm going to say about this for now, because we're going to talk about transforms more a different day. All right, now the last thing I've got for you is y equals 1 over x squared. I want to talk about this function, because this is related but slightly different. I don't think I even really want to, maybe I will make a table of values, because that is always a good strategy. Okay. So when x is 1, y is going to equal 1 over 1 squared, and that's going to be 1. X equals 2, y is going to equal 1 over 4. And we can see that it's going to go to 0 really quickly, right? Because if we divide by a square number, square gets big pretty quick, and dividing by that, dividing by a huge number gives you something really small. So, something even like 10, 1 over 100 is 0.01. Okay, so this one gets really small. But if you think about it, I'd get y equals 1 if this was -1, because I square it first, and then I take 1 over that. Right? And you square anything, you're going to get a positive number. So I can say for plus or minus 1 or plus or minus 2 or plus or minus 10, I'm going to have these same results every. But, kind of like 1 over x, the one thing I can't do is plug in x equals 0, because that would cause me to divide by 0, and I'm going to say that does not exist. I'm not really going to need any room for negative y values, because I'm only having positive y values. So in many ways, the graph of 1 over x squared looks a lot like 1 over x. It's just maybe a little more dramatic. But then over on this side, it's just also positive. And really interesting commentary I got from one of the people in my Algebra 2 class was saying basically, well, it's because you got a double root down there, you'd expect it to have the same behavior at x equals 0. And actually, that's exactly what's happening. Because this is a double root down here, we would see kind of like a bounce-ish type thing. We've seen that before in this class, so I really like that. I appreciate that. All right, that's all I got for this video. Thanks for watching. Hope it helped.